I'm Kim L. Johnson, and I'm a chemical engineer. I grew up in the Air Force with a colonel dad who developed, from a project management standpoint, liquid-fueled cryogenic missiles. You know, they use liquid oxygen and liquid fluorine and hydrazine and all that. And there he would tell us about accidents that would happen because they're pretty hazardous chemicals. The title of my talk is Rare Earths and Regulations Throughout the West. West in quotes means most any place outside of China. And that's how China views it. You know, they're in China, and then if it's the rest of the world, it's ROW or something like that. Rare earths and regs throughout the West, and you know, reg is a chemical engineering jargon for regulation. Catalysts, chemists, chemicals, and life-saving fluids and/or composites enabled not only by rare earths, which is but the tip of the iceberg. Rare earths are just a symptom of a bigger problem. That's what I'm going to speak on today. Just a few examples, just actually 3 of them. So I'm going to ignore that plus a slew of other obscure elements and their cool compounds. Catalysts and chemicals and things that make our life better and safer are essential for keeping our country safe and prosperous. That is, employed productivity and not financial wizard-wise. And unfortunately, the regulations made with poor technical and economic inputs, plus regs pushed and promulgated by entrenched interests, abound throughout the West. And, you know, why are certain things regulated so ridiculously? Here's an example of some catalyst chemicals and life-saving fluids and composites. You know, just materials, nondescript, they could be solid, liquid, or gases. And besides being essential for our prosperity, our life has been made miserable by mal-formulated regulations. Overreach, and sometimes I like to say überreach, by regulatory bodies and irrational regs that for generations have gone unchallenged, even though they're stupid and everyone knows they are. The final nail in our collective coffin have damned us in the US and in the West to the point that we have lost our industrial base, and I can see it over the past 20 years very dramatically, and thus our ability to compete in this world. First example of the Titanic reg iceberg of the West, gadolinium, GD abbreviated. I like to call gadolinium GAD like the medical technologists do because it's so important to doctors in nuclear medicine, and it's a major fission product. To a thermal neutron, GAD 155 and 157, which comprise 15 and 17% of natural GAD, look as big as 65 and 255,000 barns. So, you know, like we thought boron, lightweight boron was bad at 5,000. Well, you know, this is 65,000 for the lighter weight gadolinium, and 225,000 barns, you know, one tenth of xenon 135's barnage. Gadolinium compounds, its isotopes, hold the 3rd and biggest barn record of all the isotopes immediately after the 2.65 million barn xenon 135. But the half-life of the latter is less than 9.2 hours. So, you know, if you don't get it out of the reactor, you know, you have some nice cesium-135, but that's fine. It won't go anywhere. It's just like in the reactor, it thinks it's cesium-131. So, but what good can these big barn GAD isotopes do for Ms. Science? Well, they are a dependable source when there are slowed down neutrons nearby of high-energy gamma rays. And by high energy, I have a little asterisk there, and I have a little limerick to remind what high energy for MSRers means. At least 5/3 MeV. And so that's easier to remember than 1.6667 or something. GAD 155 sees a neutron, and with its 65,000 barn appetite, it goes really fast to 156 meta gadolinium. But that meta thing has a half-life of only a little over a microsecond. So therefore it relaxes, and when it relaxes, it goes to good Gad 156 with only 1.5 barn. That's, you know, just 3 times more than nice sodium. And it gives you one big gamma ray that's 2.14 MeV, which is definitely bigger than 5/3. Neutron imaging means the process of using neutrons to make an image when X or gamma rays won't work, like in the case of rubber O-rings in hot rocket motors. And if Morton Thiokol had, when they were Morton Thiokol had neutron imaging, they would have seen those problems in their stationary test rigs, where you can, aim a neutron beam at these things. It's basically impossible to have neutron imaging without gadolinium. A nation hoping to have successful space programs must be able to get enough Gad for considerable 300 millimeter thick foil, which is just thick enough to absorb more than 90% of thermal neutrons that strike it. Isn't that amazing? That's way thinner than aluminum foil. When Gad is activated by neutrons or MRI magnet, because it's a little magnet itself, it is about the baddest bully on cancer. Depending on what sequestering agent that wraps around the gadolinium, it goes to different organs. The second example is antimony. In Latin, they called it stibnium. And Sb is our Latin inherited symbol for antimony. It forms these following flexible features, in its compounds. Very effective extinguishing agents for typical air-fuel fires. Better than halon, and it doesn't get in the environment, and it's not toxic like arsenic. Stib comes in 2 natural flavors. Stib 121, which is 57% of natural, bearing 5 3/4 barn, and Stib 123, which is almost as plentiful, 43%, and it has almost 50% fewer barns, 3.8. Stib 3, that means, antimony 123, the heavy one, is documented to emit a gamma greater than 5/3 when it gets a neutron, and it's not going to be a neutron hog, but it will be a good denaturant because its pentafluoride boils azeotropes with uranium pentafluoride and hexafluoride, and you can't really separate them physically. You'd have to dissolve everything in water and start over again, and I don't think terrorists and unsophisticated mechanical engineers could do that. The heavy Stib sees a neutron, it goes to 124 antimony, which with a half-life of 60 days, just 2 months. And you wouldn't want even 1% of antimony to be 124 in anything that you were trying to take off vapor phase and without super-duper protection, because look what happens when it turns to tellurium 124, which only bears, which bears probably a few more barns than lightweight antimony. It gives off a 1.7 MeV gamma. It's only China who currently separates Stib 3, undoubtedly for xenonuclear purposes, but they've stopped doing it like 10 years ago in the West, and it's very good. The Chinese produce heavy enriched antimony pentafluoride, or Stib penta, if you want, you want to save syllables, and it's a valuable Lewis acid. And if you want to find out what Lewis acids and bases are, beryllium, fluoride, and other beryllium salts are the most important Lewis acids in non-nuclear or nuclear molten salt science. And it melts at 8 degrees C, like cold water temperature, and boils at 150 C. So even though a reactor is somewhere around 600 or 700 C, that antimony penta is such a strong Lewis acid, it will borrow a fluoride from FLiBe or something, so it can be hexafluoroantimony anion, and that's even a stronger binding constant than uranium penta or uranium hexa, which cannot leave from a bath if you have like three or more sodiums per Lewis acid in that bath, and you will never get the uranium out. And so this stays in the bath, but if you're trying to pull off UF 5 or 6 for plagiarism or something being nasty, that will come with it, and it will have rad stuff that has a short half-life. It will be as bad as the aged daughters of U-232, but it's a lot cheaper than ionium. It's easy to make. Look, all you have to use is a simple atmospheric fractionation column with, it doesn't have to be very tall, just cooling water or silicone at the top. You probably wouldn't want to use water because when it mixes with water, it makes a violently strong acid that's millions of times stronger than sulfuric. So nobody in the West bothers to make it, but it's the easiest thing in the world. Here's the real reason for the Sino-antimony monopoly. And this is kind of a scandal, and it should put the EU regulators to shame. Just 0.5% each of Sino stib oxide, trioxide, Sp2O3, and covalent chlorine and or bromine, attached to carbon, in the polymer as flame retardant. And so vinyl chloride, has way more than several percent of chlorine. And everything co-extruded with otherwise highly flammable plastic siding. Had the antimony monopoly not confined the production of safe siding to China, it would have avoided this inferno. And the Brits had a tough time getting hold of it without paying for, single-use shipping or something, and so they went for the cheap, and people burned up in the Roman candle. Antimony is very clever. The trivalent antimony oxide loves to absorb HCl and HF and HBr and become hydroxy halides. So when the fire is starting to go and the vinyl chloride starts making HCl, or if you have a bromide fire retardant, it makes HBr, it is absorbed by the slightly alkaline trivalent antimony oxide and turns into antimony oxychloride or antimony oxybromide, and it's a linear molecule, and in the heat of the flame it vaporizes, but it's not like aqua regia, which has nitrosyl chloride. It's electronically equal with nitrosyl chloride, which is O double bond N, Cl. This is O double bond SbX. When it gets away from the flame and cools off a little bit, suddenly it says, oh, I need to be a polymer because I'm one of the heavy elements. So it polymerizes and makes this oxyhalide polymer that will not burn, even though the antimony could be pentavalent. It would rather be trivalent, like lead would rather be divalent than tetravalent. So it reprecipitates on the surface of the polymer and puts inorganic seal on it, and no more molten vinyl or polyethylene leaks out. So you wouldn't have these fire waterfalls. Now they're going to be forced to buy it from China and pay double if they could just have the raw materials in their own country to compound them with the extruders. The third thing, beryllium or beryl. It's an excellent and flexible Lewis acid in the form of its solo salt. So if it's just a beryllium chloride or fluoride, it's acidic and it will dissolve in water and give you an acid reaction, but it won't necessarily hydrolyze in the case of fluoride because it's such a strong bond. It's like a sugar molecule in water. So if you drink it, it won't digest because it's too polar. It'll just give you diarrhea like Epsom salts. And it really has to be complex beryl salts. Those are the ones that are essential not only for strictly chemical molten salt science, but especially for nuclear Ms. science. And that's my abbreviation for molten sol ciencia. It craves 2 Lewis male electron nodules, be they on water or loose fluoride ions from lithium or whatnot, because the beryl has to be tetracoordinated always, always. This excellent, it's added economically. The only economical way to add beryl to your bath is solely in the form of a complex beryl, like where you have beryllium with X, it could be chloride, fluoride, or a single oxygen bond taken twice, but you need to have at least 1 more or 2 more on that, or somewhere in, like 1.5, and it should equal 1.5. Otherwise, it won't be handleable, and it will be like taffy, and you'll never grind it, and you'll never get it melted. This excellent Lewis acid is essential not only for strictly chem molten salt science, but especially for nuclear Ms. science, of course. And here's what makes beryl so unique. Beryl coordination beyond monomer anions like FLIBE, be it with 2 lithiums or 2 sodiums, it has the ability to rapidly interform cyclic trimers and tetramers, plus linear oligomers. Oligomers mean like 3 or 4 or up to a dozen or so beryllium fluoride bonds in a chain, all bearing delocalized negative charge and off delaying and even inhibiting crystallization, even when way below the barrel brew's expected freezing point. So remember in Raluca's time-lapse video yesterday, we saw pictures of rapidly cooling pure alkaline fluorides, like lithium, potassium, sodium in a eutectic. Well, they're not complex, and they're very crystalline, and they're very alkaline and actually corrosive to any coating on metals because they're like molten fluorides. Contrast FLNAC with the far better pH balance and more complex fluorobarylates. And we'd rather have a spill, that took a long time and just got more viscous rather than freeze up on you. I'm not going to talk about the toxic mechanism, but there's only one structure of beryllium that is toxic to like 1.5% of the population. It's fluffy beryllium hydroxide, incompletely cooked beryllium hydroxide gel that didn't go to dead burnt beryllia, which is just BeO. And it still has some water of hydration on the surface, some beryllium OH things, and when it gets in allergic people's lungs, it rehydrates to sticky beryllium hydroxide gel. It's not soluble, and their boogers mistake it for a mad cow disease or something and start attacking, and their antibodies start attacking their own proteins because they were directed to misfold by the beryllium hydroxide. Well, beryllium fluoride doesn't coordinate like that, and any other beryllium compound doesn't do that. So the Navy is not in really any health regulation violation when all that beryllium dust from their beryllium breaks accumulates on the Navy carrier, because it's dead burnt beryllium oxide. It's not ever going to hydrate. Summing all up, the rare earths and the regulations that we have throughout the West kind of drowning out science. As a result, because of the result of stupid, idiotic regs, throughout the West, the West is drowning, economically. But I don't think our government views it that way.
Thank you very much, Ken. I really appreciate you doing it.